Okay. Good morning to everyone. Let me first start by thanking the organizers, and in particular Johanna, for setting up this very nice meeting. So my talk is about the holographic Pomeron in low-X QCD. I will be talking about some older work and some more recent paper with two PhD students back in Porto. So first, let me try to describe to you what is the basic question I want to answer in QCD. And the first thing is to describe to you what is the soft Pomerance. So if you in QCD do elastic scattering, such that what is exchanged are the quantum numbers of the vacuum, and if you look at the answer in the Reggie limit of large S fixed T, you will see that the amplitude will have this behavior. It goes as S to some Reggie pole. Usually it's alpha of T. Here I will use J of T, the letter. And this is something very universal. You do, even if you do scattering with different external particles, you always measure this behavior of J of T. This is the famous Donaghy-Lange of Pomeron. In particular, if you look at total cross sections, which are obtained from this amplitude just by taking the imaginary part at equal to 0, you see that they grow basically determined by the value of this function J of T at equal to 0, which is the intersect. So this is something very universal in QCD. Here I have total cross sections for different states, soft particles, and the leading piece is always this S to that power that I wrote here. So the idea is that this Pomeron should be associated with some trajectory of glue ball states. Pomeron also appears in deep inelastic scattering, where we look basically at the target, let's call it the proton, with some off-shell photon. Again, if we use the total cross-section can be again obtained from computing this amplitude at equal to 0. So it's basically similar to the previous case that I was telling you, but now we have this off-shell photon that corresponds to computing a correlation function with the bilinear current to obtain this cross-section. So I will be using in this context. We will be considering deep inelastic scattering in this talk, and there are two kinematical variables that I will you probably remember. But if you haven't seen this in the last years, let me just tell you what they are. So there are two important kinematical variables: X, Bjork and X, which basically corresponds to the fraction of the total target momentum that the parton has that is struck by the photon, and the Reggie limit corresponds to the limit of low X. So that's what we are going to be working on, low X. And X is basically, S is basically 1 over S. And then the other kinematical quantity is the size of our probe. We are looking at the target with this off-shell photon that has some size, and that's the Q square. Oh, sorry, that's the Q. What you see here is basically the size of our probe. Defines the size of our probe. Okay, so what happens in deep inelastic scattering at this small X regime? The parton distribution function is dominated by gluons. It's gluons that dominate the physics, so we can forget about the quarks. And there's something interesting. So it is also observed some sharp increase in the cross section with S, so with 1 over X, as should be for Reggie theory. But the intersect is varying with the size of our probe. So if you look at data at some value of your Q, so the size of your probe, and then you have several different points and try to reproduce that with some 1 over X power, you'll get some exponent. But as you change Q, the exponent grows, and the exponent varies between 1.1 and 1.4. So this raises a question immediately, which is, are we talking about the same Reggie pole as in the previous slide when I described the soft Pomeron? Or is this another Reggie region? So usually in deep line scattering, this is called the hard or BFKL Pomeron, which is not the same as the soft Pomerance. So this is what we want, the question we want to address. And we will address this question and try to understand the physics using the gauge gravity duality and like the important work to analyze, to answer this question is this old paper of Brauer, Ponschiska, Strassel, and 10, BPST, where they stated that the Pomeron trajectory of QCD is dual to the graviton-Regge trajectory in ADS or in the dual QCD. So now, as an invitation to what I'm going to tell you afterwards, let me first describe some proposal, again, by Donat and Lenshoff later on. To resolve this question, they said, okay, what's happening is that in deep inline scattering, what we have is the contribution. There are two regions contributing to the scattering. And they tried to reproduce the total cross-section with these two functions, with different powers of x. And then for each q square, they will fit these two numbers and then do it for different q squares. So you have these functions of q square. And the functions are plotted here for each one of the regions. So there's this red curve and the blue curve with the corresponding intersects. So the idea is that this running of the intersect could be mimicked by the contribution of two regions, because these functions will have different behavior for different values of q square. So you could, as q square varies, the one be more important than the other. So this is what I will be now describing later in the talk. If you apply this idea to the gauge gravity duality, to some ADS QCD model, you will find out, just by doing the computation, that these functions f have can be seen as the product of two functions. One function is known for the specific model. It's related to the wave function of the field dual to the electromagnetic current operator. So there is a gauge field in the bulk that is dual to the operator psi bar gamma mu psi. So this function is known for some specific model, times some function that is that solves a one-dimensional Schrödinger problem. It will be a function that will allow us to the Pomeron propagator using some spectral representation. I will explain later. What matters here is that if we divide this function by this guy, I should get something out of this picture that looks like quantum mechanics. So it's not a coincidence, but it happens. So after we actually did all this fitting and what I will describe later on, this is the first thing we went to do, and it actually, qualitatively, if I divide by the proper function, this thing really looks like a ground state and is the first excited state. So this is qualitative, but it was a very good sign that we were in the right track. You really need to divide by this specific function to go from here to here. Okay, so now let me try to describe to you the computation, and I will start first with the simple case of pure ADS. So if you want, this will be n equal to 4 superambulars. We need to do Regge theory. That is, we need to consider the exchange of spin J fields and then resum all of them by doing Sommerfeld-Waltz and transform. So let me consider exchange of a spin J field in ADS. So this is the Witten diagram. We have our electromagnetic U1 gauge field that is dual to the electromagnetic current operator, some exchange of spin J field, and some target that later on will correspond to some normalizable mode that will be associated with the target. And what we are doing in the Regge limit is some really ADS scattering process where particles are basically moving very fast across the ADS cylinder. This correlation function can be written in some impact parameter representation. And what is important here is that we have an integral of Z and Z prime that corresponds to the two interacting points. We have the external wave function of the external states. They can be normalized and non-normalizable fields. And then we have a function that is what has all the information about dynamics, a function of two variables, S and L. If you do this in conformal field theory, these actually are the two related to the two cross ratios. In the case that we are in the Regge limit, these functions have a very specific form, which is the form that I'm writing here. So what is this capital S? Capital S corresponds to the energy squared with respect to the global time in ADS cylinder. That's this S. And the capital L is the impact parameter in the impact parameter space, but is in ADS, that is a curved space, so it's actually the impact parameter on a three-dimensional hyperboloid. Is this space that is obtained from the intersection of these two node surfaces. So this line here. Usually the impact parameter space is just R2 in flat space, here is a three-dimensional hyperboloid. Okay, so now let me tell you about what is this function G of this function of the impact parameter. If you go and do the computation, this function is obtained from integrating the propagator of the spin J field along light rays, and actually it solves in impact parameter space a propagator equation that is written here for some scalar propagator. So now, in order to find this propagator, we can actually now rephrase this problem in terms of Schrödinger problem. If I basically look at this operator and act on this function, I will see that it acquires just the problem of a one-dimensional Schrödinger problem, the form of a one-dimensional Schrödinger problem. And in the case of ADS, actually the potential is just 1 over z squared. But notice that this potential depends on the dimension of the operator that I'm exchanging. So for a given value of j, the operators, the dimension will be along this line. There will be the unitarity bound, and the operators for this will be the energy moment tensor exchange, which has protected dimension 4. Notice that this is delta minus 2. And then you have the other even spin fields that are exchanged. Okay, so now I will try to apply these ideas in the context of some model that mimics QCD. So my background, I'm interested in the QCD vacuum. My background will have this form. These are these two fields. And I will use, to be definite, just a specific model of Elias and the collaborators, which is based on 5-dimensional dilaton gravity model. So let me just tell you, the reason we use this model is that this model was done to fit the lower spin glue ball masses, and we want to do exchange of glue ball masses, of glue balls. It's a phenomenological model that has a number of parameters which they fixed. We used those parameters. We didn't play with that. So we just took it as our toy QCD, if you want. Let's see what happens. Furthermore, since we will need to consider a spin J field in this background, in this theory, and we will need to understand also, have the coupling between the current and the spin J field. If we were in a conformal field theory, there will be only 2 OP coefficients, and that's it. For example, for the graviton, the case J equal to 2, if I write this effective action, I could write something else here with different powers of the curvature, but in ADS, this will just reduce to these 2 local couplings. It cannot be anything else because there are only 2 OP coefficients. So what we did here was, okay, let's just generalize this, just putting derivatives here in the middle acting on these fields F, and write these local couplings to our spin J field. If I was in ADS, this would still cover all possibilities. Since I'm not in ADS, at the end of the day, then there will be more possibilities, different dependence on the z coordinate. I will just stick to this. So now we are going to do an exchange of a spin J field. So we need to understand its dynamics. Is the field that will be dual to this gluonic operator that is exchanged. So I need to write the equation of motion for this spin J field. In fact, I will only be interested in writing the equation of motion around slightly below J equal to 2, because after doing the Reggie theory, what matters is the behavior at the Reggie pole. So in general, I will write so I have to basically decompose this field that will be a symmetric traceless transverse field. I will have to decompose it in the reducer representations of the symmetry of the boundary, and then just consider the equation of motion for the propagating degree of freedom. And I want an equation that in the ADS limit reduces to the usual case for a spin J field in ADS. And in J equal to 2 reproduces the TT fluctuations of the graviton of this ADS QCD model. So this is the equation we wrote based on the spirit of effective field theory. For now, forget the lower line because they are zero in because this line is zero in these two cases. So if I have in the EDS case, there will not be this term. This combination here is 1, and I recover that equation. If j is equal to 2, this guy will be 0 because dimension of the gravity of the energy moment tensor is 4. And I will get these three terms, which is precisely what you obtain if you do the fluctuations of the TT part of the metric in that background. In general, we will have this term. So I wrote here j minus 2, so it is 0 at the graviton. If we are in ADS, all these combinations are 0. So we need to, there's no problem. And basically here I wrote every possible term that is a two derivative term. So it's in the spirit of effective field theory. It's all that I can write. Now, these constants A, B, and C will be fitting parameters of my model. Notice that they could be functions of J. But so if I was totally honest, I should write there A of J, B of J, and C of J. But since we are, but it will be a mess. So I will just put them as constants. And since we will be working around j equal to 2, let's just leave it as fitting parameters because just for the sake of simplicity. Then we still have another thing, which is this dimension depends on the spin j that you are exchanging, and the dimension of the operator as some function of j. So here we take our intuition from what we know from n equal to 4 superambiguous. The dimension of the operators has this form of this curve. It's a quadratic curve. Infinite coupling would be this horizontal line. Zero coupling would be the unitarity bound. Even in QCD, this curve actually has this shape and is also quadratic around this point, which is for us what it matters. So I will write this curve as in this quadratic form, forcing it to pass through the point of the gravity, and that's the energy moment tensor is conserved. So it has this form. Let me first tell you that first we have this parameter that actually defines some scale. And the one here is the term that BPST considered in their first paper. This is the term that will, if I take the flat space limit, this will reproduce the Venezian or Regi behavior of strings in flat space. The next term is just a 1 over square root of lambda correction. And why did we write this term here? We wrote this term so it's just to force the right asymptotics. If you want this field to, near the boundary, have a behavior that will correspond to operators that are at the unitarity bound, because at zero coupling, these operators have dimension j equal to j plus 2. They are these two operators. You need to add this term. So this is so basically it's to fix the correct boundary condition in UV. So this is the equation we will be working with. So now I need to compute this Witten diagram. So morally or implicitly, I'm doing it for each spin j. Okay. This will be the propagator that, as I told you before, can be recast in terms of a Schrödinger problem. So as I vary j, the potential will start, in particular, going down. So this is j equal to 2, then j equal to 1.5 starts going down. For j equal to 2, what you see here is the energies of the two glue balls that were fixed by the SQCD model. But now, if I start coming down, these energies come down, and in particular, when this energy crosses 0, that will be the value of the intersect for the first Regi trajectory. Then if I further go down, this guy crosses 0 will be the value of the intersect for the second Regi trajectory. And for this propagator in the transverse space, we just, once we have this written in terms of a Schrödinger problem, we just use the spectral representation of the propagator. So this is what we are doing implicitly. I have all these contributions for different j's, but then I do a Sommerfeld-Walton form, and I pick up the poles at the Regi poles. And the behavior at each of these Regi poles will be given by the analytic continuation of this propagator that is governed by the equation that I wrote before. So that's the logic. So at the end, you get the following answer. You get that your structure function, the total cross-section, if you want, has the behavior, the following behavior. So it's a sum of contributions of Regi poles. There is the 1 over x or s dependence, as it should be there. And then there will be some two functions of Q square, the size of our probe. There's minimal coupling contribution and the non-minimal coupling contribution. So let's look first at the minimal coupling contribution. What is this function here? For now, forget this coupling in the front. So there's an integral over z. This is the point in the holographic direction of the interaction between the spin J field and the U1 gauge field. So we are integrating. These f's are basically related to the non-normalizable mode of this U1 gauge field in the bulk, and here you have the shape of the function. And this psi is precisely what comes from the propagator of the spin J field that is exchanged. In the spectral representation will be a function of that point here. So that's wave function, psi of z. The non-minimal coupling is similar. The only difference is that since the local coupling is a bit more complicated, there is some differential operator that acts on the Pomeron kernel. Well, it has with some derivative. It's what it is. I just wanted to point that out. Finally, what are these couplings here in the front, Gn and G tilde n? It's the same thing as I was describing, but it's for the other interaction point when you have the target being exchanged, as an interaction between the target and the spin J field. So again, there is an integral over ADS. So here it's good. I don't know anything about what would be this normalizable mode associated with the target. In this case, the proton. But it's not a problem because this is fixed in our all the data that we are going to analyze is always the same target. So this thing integrated still against the Pomeron wave function doesn't matter. This will be a number. Okay? So it will be a fitting parameter for me. It will be a number. For example, here you have local couplings that, depending on the spin, that are analytic continued when you do the Walton-Sommerfeld transform. I don't know what that is, but it will just be a number. At the end of this thing, it's going to be a number. So now let me tell you what describe our results. So we consider data in the low X region. So we just cut off all the data for X to be smaller than this number. There are 249 data points covering a very large region of Q square, including the weak coupling region. So we kept the first 4 edge trajectories to do this fit. So there are like 4 Pomerons. They are all above the intersect of the mesons that will also contribute to this process. So they are above those, that's why we can put them. There are a number of fitting parameters. I don't have time to give more details, but what is important here is that we did this fit, and the chi-square per degree of freedom is 1.1. So it reproduces the function that we got, reproduces it. In particular, in the region of small Q square, where QCD techniques, they just put there a cutoff, and they say above some value of 4 GeV, they just don't. Below that value, they just take out the data because they cannot reproduce. So let me now say some things about these results. So the first thing is that we reproduce this running of the effective intercept precisely with this contribution of several Pomerons, as initially suggested by Danagel and Joff. When the Q square we have a very soft probe. This is basically the soft Pomeron behavior with an intersect about 1.0809. If you increase Q square, you get the intersect increases and you go what people call hard Pomeron. Moreover, what was quite surprising for us is that after fitting all this data, which is obtained from the value of our amplitude at t equal to 0, okay, so that the parameters were fit just from scattering results. We can, since we can vary our potential and see how our edge trajectory is varying with J, we can just plot the edge trajectories. So this is the plot of the edge trajectories. This is like the first one, the first Pomeron. This will be like the second Pomeron, and so on. The fact that these two curves pass in these 2 points, it was an input of the model because we used the model that reproduces the low-lying spin tubular balls. What was surprising is that these curves have this shape. They are not linear trajectories, they have this behavior. And they somehow go past around the points of the lattice QCD prediction for spin 4 and spin 6 blue balls. It just happened. We just, at the very end, we went to check it to see what happened. In green here, you see where the meson trajectories are that also have vacuum quantum numbers. They will also contribute to this process, but the intersect is slightly below. Also, the scale of the coupling that we put for non-minimal coupling is of the order of the gap between spin 2 and spin 4, which is expected from effective field theory, and particularly this paper. So let me just conclude. The first thing is that I think we have like a picture that is consistent with this understanding that the Pomeron has several trajectories, which in ADS just comes from quantizing the gravity in a box. And it's consistent, our ADS QCD is consistent with that. We can explore other processes now using this picture that we are advocating that are available. We haven't done it so far. So there's these other processes that are very similar that were already studied in the past. We should include meson trajectories to make this picture more complete. It can be that after including meson trajectories, we actually don't need the 4 Pomeron trajectories and the numbers will change. This is phenomenology, I really don't know. Then it will be interesting to consider the coupling of the Pomeron to gluon jets. At LHC, they have this forward program where they will be doing forward physics, and in particular, there's a process where from the Pomeron they can come out some jets at some definite rapidity gaps, and so maybe it will be interesting to analyze that. And of course, I mean, we haven't tried yet, but of course, this should be something generic. I think if we have some other sensible ADS QCD models, the results should also work well. We are not doing precision QCD, so this should still work. Okay, thank you.
Yeah, thank you very much for your nice talk. There are questions, please.
Can you go back to the first slide?
To the very first. Wow. You could have interrupted me that.
So the point is that...
This one.
Right. So the point is that in addition to this s to the 0.8, there is also another term which is s to the -1/2, which describes this decreasing part, right?
Yes.
Right, and no, the decreasing part, but that goes on. It seems to me that it's an exchange of a light meson like a row, and therefore you have this intercept which is 1/2, and then there is an exchange of a glue ball. You argue that it's maybe not only one, but a mixture. But a glue ball will give you, since it has the intercept is twice the one of a meson, it should be 1. So instead you get 1.08. Okay, I mean up to 10%. There is no reason that we can really predict. So I think that the naive picture is that it's an exchange of a meson and an exchange of glue ball. The surprising fact is the reason that alpha prime is a quarter and not a half. But as you explained it, because of this, in this differential cross-section, you will see that this quarter. But since we have this interpolating between the linear behavior and the flat, then in between we will get also in some place a quarter. So it's not so surprising, I think.
I think I agree with your comment.
Further comments, questions? Oh, yeah.
Thank you. So for these low energy data, or low Q squared, you definitely need a F2 meson to include it. That's known from the Hera description. But my question is about this Donicky-Lanzov model. This uses a coupling of the Pomeron to the external particles, which is a vector coupling.
Yes.
This is done by hand and actually contradicts quantum field theory because you get negative cross-section for antiparticles, necessarily. So the correct thing to do would be a tensor coupling of the Pomeron to the external particles.
I mean,
what is the coupling of the Pomeron to the external particles in your model?
So what are you talking about? We did the computation holographically. right? I don't know if you are talking about some.
I understand. So
What the coupling was just like minimal. Take the minimal coupling. Take the graviton. Start at spin 2. Take the graviton. So your action will be f squared from your U1 gauge field in the curved space. Linearize it, and the coupling will be FH. That's the minimal coupling. And this is known that it will reproduce, if you compute like Witten diagram for a 3-point function, you will reproduce the OP coefficient and the correlation function of a CFT.
Yeah, I understand.
And then you can also consider the non-minimal coupling. Do also for the graviton, and the same thing holds. And yeah, I don't see.
So I'm talking about the boundary theory coupling, right?
Yeah, but
that comes out effectively. So that
we did the computation in a bulk.
Okay,
we didn't do it in the boundary theory. So
but there are actually rig data which favor tensor Pomeron by 10 sigma or so. So this would be interesting to see whether that comes out.
Maybe we can talk later, and you explain what you.
Okay. So, are there further questions? That seems to be not the case. Then Johanna has another announcement.
Well, just quickly about the conference photograph.